Okay, now, how does this relate to engines? So the way that you see how an engine operates, the way that you visualize how an engine operates is you plot the thermodynamic conditions inside your cylinder. So here is your cylinder. You have a piston that allows the volume to expand. Okay, and you have a working substance. So you have a gas that's inside the piston. Okay, and then what you want to do is analyze how do the pressure and the temperature and the volume relate to each other inside this cylinder. So you have pressure and temperature is the typical, not pressure and temperature, pressure and volume is the typical plot that you will put on this thing. So you can raise the pressure, you can change the volume, and they're going to be related to each other. And if it's an ideal gas, which not everything's an ideal gas, but we can pretend for the moment that it's an ideal gas, then the pressure and the volume are related to each other with PV equals NKT. Okay, so here's a question. Is fuel injection into an engine cylinder considered a gas or small solids? In this case, when you inject fuel into the system, it doesn't really change the gas properties that are in there. So they are small droplets that go in. So they're not really atomic, right? You're going to have these droplets of things that go in, but the amount of fuel that goes into the cylinder compared to the amount of a pre-existing gas in the cylinder is relatively small. So it doesn't really affect the thermodynamic properties. Okay, so now what you have is, remember that pressure times volume has units of energy. And so if you have a cylinder that's going to follow some trajectory on this pressure times volume thing, then the energy in that transition is going to be the area under this curve. Okay, so let's say that you have some pressure and the pressure and the volume are going to vary over time. So like time is ticking in this direction. So you start here and you go over here. What's going to happen? Well, the volume is expanding and the pressure is declining. Okay, and that if the volume is expanding, then that's going to be pushing. The only way for the volume to expand is to either blow the cylinder out or to push on the piston. So you can push on the piston, and if you're pushing on the piston, then you can extract that energy and use it for your own nefarious purposes. So that you can have like a take over the world machine attached to the cylinder, and as the pressure declines and the volume expands, then the expanding cylinder can drive your take over the world machine that's up here. So you can extract that energy and take over the world with it. So that is what's happening as you go from one point to another on this place. If, on the other hand, you start here and you work your way backward, now time is ticking in the opposite direction. So if you start with a big volume and you're increasing the pressure, so the volume is getting smaller and the pressure is going up, then that is taking energy from your take over the world machine and putting it back into your substance. Okay, so if you're going backwards, then you're depositing the energy back into the substance, and if the thing is expanding, then you're taking the energy from your substance and putting it back into your take over the world machine. Okay, let's see. So typically what will happen, why is someone bothering me? Typically what will happen is that you'll set up a cycle. You want to go through some repetitive cycle where you can constantly extract energy from some substance and put it into your take over the world machine. Okay, so you'll have a pressure times volume diagram, and you'll have some cycle. Here's your cylinder again, and you have some way of manipulating the properties of the gas in order to change the thermodynamic situation. So a common one is called the Autocycle, OTTO. It's actually, it's not an acronym, it's OTTO like this, named after some Danish, I think it's a Danish guy. We'll call him Scandinavian, and then I'll be mostly right. So the Autocycle, what happens there is you open up a valve to the ambient air, and at constant pressure, you then draw that air in. So you have a cylinder in here. So the cylinder is usually, in this case, powered from underneath, or we'll have it from underneath because that's the way that I drew it. So you'll draw air in into your cylinder. So the volume at constant pressure, so it's atmospheric pressure coming in, and the volume of the gas in your cylinder is going to expand. So the volume expands like this. Okay, then you seal it off. Then you close the valve, and now you have all this gas trapped in that cylinder, and you're going to do it. You're going to have your way with it. So the gas comes in, you trap it in the cylinder, and now you can do whatever you want with it. So you're going to take that gas. That gas is going to have some adiabatic coefficient that is the ratio of the heat capacity at constant pressure to the heat capacity at constant volume, which is going to give you the curve that it's going to follow as the gas gets compressed. So now you're going to take that gas and you're going to squeeze it. You squeeze it and raise the pressure. So you squeeze the gas and raise the pressure, and it's going to follow some curve that's related to the heat capacities, right? So you're adding energy to that system by basically driving it, by doing work on it. You're exerting a force over a distance. When you have particles that are bouncing around on it, you're pushing the surface up against it, which is causing the ricochet to happen with slightly more energy than the particles came in, and so you're adding energy to the system that way. There's a lot of ways to think about it. They're all, as long as you do it right, they're all right. Okay, so this thing expands and you get up to here. So now you have this pressure up here. It's a higher pressure situation with all the gas compressed at the top. Then you change the chemical composition without really changing the pressure. You're adding a little bit of fuel to it, and then you light it on fire. When you light it on fire, now you're all of a sudden releasing all of these bonds, all these chemical bonds are released and drives up the temperature. Okay, so when you drive up the temperature, the volume stays fixed, right? You're at the apex of the compression. Volume stays fixed. The temperature drives the pressure way up. You increase the temperature and the pressure goes way up. Okay, and then the cylinder is allowed to expand. So then the cylinder expands and the volume expands as the cylinder expands and the pressure drops. Okay, and then you get down, now that everything is down here at the bottom, and then you open up the exhaust valve. You open up the exhaust valve, the pressure drops, and then you push all the stuff out at atmospheric pressure. So this is atmospheric pressure. You push all that exhaust gas out, and then you draw in the next cycle. So this is the cycle that you get for the Autocycle. It's 4 cycles, the intake cycle, compression, and then there's an important step that's not one of the cycles, which is you light things on fire, and the temperature goes way up. So this is, in this case, you're manipulating the temperature by causing a chain, like a chemical reaction to take place, where you're exchanging the bonds between hydrogen and carbon, typically. So you have a hydrocarbon chain where you have carbon and 2 hydrogen atoms like this in your extended hydrocarbon chain, right? Depending on the length of your chain, you might have octane or something like that. And so these bonds, the chemical bonds between hydrogen and carbon, have some amount of energy associated with them. The chemical bonds between oxygen and hydrogen are stronger than the chemical bonds between carbon and hydrogen. So this is oxygen and hydrogen is a stronger bond than carbon and hydrogen. So if you can break these bonds and replace a carbon with an oxygen, then it will bind with more energy, and it releases that energy. Like when it binds with more energy, it gives up energy to the environment. That release of energy into the environment is going to change the kinetic energy of the particles. It's going to increase the kinetic energy of the particles, which are then going to allow the piston to be, to drive the piston. So this replacement of the hydrocarbon bonds to the oxygen and hydrogen bonds is where the energy comes from. So basically, if we were to look at the bonding structure, you would have something that looks like this. So you have a carbon-hydrogen bond here, and you'll have an oxygen-hydrogen bond here. But in order to get the carbon-hydrogen bond to break apart, you have to add a little bit of energy. So you add some energy to the system to break the carbon and hydrogen bond, and then when you form the oxygen-hydrogen bond, you release this much energy. So you have to give up some amount of energy to make it over the hill, and then you get back this much energy as that bond forms. And so where does that energy come from? Well, part of it is that you compress the gas, and so you increase the temperature of the gas by compression. And then you have a spark plug that adds this energy. And then what happens is you only have to get this started. You only have to start getting a few things over, and then the energy that's released in the formation of these oxygen-hydrogen bonds, and its carbon-oxygen bonds. So oxygen-carbon and oxygen-hydrogen, those bonds collectively have more energy than the carbon and hydrogen bonds that you started with. And as you release this extra energy, that can also contribute to breaking apart the carbon and hydrogen bond. So all you have to do is start the fire, and the fire itself will spread because it's releasing energy as it goes. So that is fundamentally what's happening when you do this. So you're rearranging the bonds among the chemical elements that are trapped in your cylinder in order to release this energy, and then you drive the piston, and you extract this much energy from your cylinder, and then you can take over the world. Now, this is not the only way that you can have an engine work. So the diesel cycle, and I can never spell it right, I think it's diesel cycle. It looks the same, but it is not the same. So in a diesel cycle, you have the same pressure volume like this, and you'll have the same intake. You have the same increase right here. Well, that's kind of ugly, but same increase in pressure, but the compression ratio is a lot higher. So diesel engines, the Autocycle will have a compression ratio of like, what, 6-to-1 or something like that. So you'll compress, the amount of volume in the cylinders would be, 5.0 liters or something like that, or 4.6 liters or whatever the size of your engine is. The compression ratios here are going to be something like, was it 9 or 10? I don't remember exactly what it is, like 9 or 10 for an Autocycle. For a diesel cycle, they're more like 15 to 20. So you have a higher compression ratio, which means that the pressure at the end of the compression is a lot higher, and as a consequence, the temperature of the gas is a lot higher. And so you don't need a spark plug. You have a glow plug that contributes a little bit, but you don't have a spark plug that sets off the burning process. The compression ratio is sufficient to ignite the fuel. And as a consequence of that, what happens is the cylinder expands more slowly. The gas burns more slowly. And so you get this period of time where the cylinder is expanding and the pressure is maintained at a constant rate, and then it declines back down like this, and then it goes back through the intake, or the exhaust and intake cycles. Would you always use a piston? Well, a piston is the easiest way to extract the energy. So this is what the diesel cycle looks like. An advantage of the diesel cycle is that the pressure goes up slowly in this case, like slowly meaning like 1,000 times, what's RPMs, like 1,000 times per minute. So a few thousand times per minute it goes up here, but that's slowly compared to the sound speed traveling across that. And then the expansion, as the gas burns, the cylinder's are already expanding, and so the pressure stays constant as the gas burns. This type of engine lasts a lot longer because in the Autocycle, when it comes in like this, and then you have that sudden spike in pressure, that's where the damage comes to your engine. Is that all of a sudden, as quickly as the flame passes through the cylinder, the pressure jumps up very rapidly, and that's causes strain on the sides of the cylinder and stuff like that. So anyways, that's why diesel engines last millions of miles, where OTTO engines will last hundreds of thousands of miles. Diesel engines last 10 times longer than Autocycle engines. Let's see. There are other ways that you can do this, is through like a compressor. So you can have the way that refrigerators work is a little bit different. So with a refrigerator, you'll have a compressor on it, and it will drive a gas through what's called a throttle. So in a line, you'll have a small aperture. Okay, and then you compress the gas on this side of the aperture, and then you get a rapid expansion of the gas on that side of the aperture. And the rapid expansion of the gas causes the gas to lower its temperature. So you can tell basically this throttle is acting the same way that your lips do when you're cooling off like a spoonful of soup. So you have a spoonful of soup like this, and the soup is too hot, and so you blow on it, you purse your lips and you blow on it. And so even though the air coming out of your body is at body temperature, it's at 98 degrees, when you compress the air and then you at high pressure, so it's high pressure back here, and you blow it through a small aperture into a low pressure environment, that air is going to expand, and as it expands, it loses energy, right? It gives that energy up to the environment. It gives that energy up to pushing away the atmosphere. And as it gives up that energy, then the random motions will decline. And as the random motions decline, then the temperature goes down. And so you purse your lips, you blow across the spoon, and the air that comes out of your mouth as it expands cools off. And the same thing happens here. As you have a compressor, it drives the gas, or your refrigerator substance, through this throttle. And as the gas expands, then it cools off. And so that's how you refrigerate things. Everyone just blow at the same time. Exactly, that's what it does. So why do diesel engines generally sound more? Like, why are they louder? In general, diesel engines, they're probably louder because you have a bigger compression ratio. It would be my guess. So I'm not really sure. Is gas cools down? If gas cools down while you blow, then so it comes out. So air, when it comes out of your body. Well, here's the experiment that I always have my students do. If you need to warm up your hands, it's not recommended that you do this because you're adding humidity to the system, and then the water condenses, and then that causes your hands to cool off again. But if you step outside, people blow into their hands like this to heat it up, and there they have their mouth open. So they're not changing the pressure of the gas. So they're starting at atmospheric pressure, their mouth is open, and they're expending the air at atmospheric pressure. So it's coming out at 98.6 degrees. It's coming out at body temperature. Okay, and so the difference between having your mouth open, where you're not changing the pressure, you're not manipulating the pressure away from atmospheric pressure, is it comes out warm. But if you purse your lips, and then the gas comes out at high pressure and expands into the ambient environment, then the pressure drops and the gas cools off as it drops. And so that's the difference, right? It's how you can have your body temperature air both warm you up and cool you off. So let's see, why is higher grade octane resistant to premature ignition? That's a good question. So different gases, like I think butane is another example. Certain hydrocarbon chains are going to be more tightly bound. And so they're a bit harder to break apart. So certain lengths of hydrocarbon chains are harder to break apart than others. And so because they're harder to break apart, it takes more energy basically for them to burn, to split everything apart and to convert it into, you get water and CO2 out of it. And so like a butane, I think it's a butane ring. This is chemistry stuff and nobody likes chemistry, so I don't know all the details of this. But I think these are particularly hard to break apart, butane rings. And so this will take longer. You have to add more energy to the system before it will break apart and start to disassociate. And so that's when you change the amount of octane that you have relative to whatever the other things are in it, propane, and you have a variety of lengths of hydrocarbon chains. So basically what you do when you make gasoline is you take your crude oil, and it's got everything in it. It's got methane, so that's CH4, and then you've got whatever comes after that. You have all these different hydrocarbon chains of different lengths. Okay, and there's some lengths are gigantic. And then you take that crude oil and you boil it. And what happens is that the lighter stuff boils more readily than the heavier stuff. So the heavier stuff, not only does it not boil very much, but because they're so heavy, they don't move very fast. And so they can't escape to high elevations. And so you have a tower, it looks like this. You have a flame under here, and you put the crude oil in and you boil it. And the heavy stuff stays in gaseous form down here, and the lighter stuff is able to float higher and higher and higher. And that's basically corresponds to the length of the hydrocarbon chains. So the shorter the hydrocarbon chain length, the more rapidly it's going to be moving. It's got a lower mass at a given temperature, and so the velocity is going to be higher. So because the velocity is higher, it's able to escape up to higher elevations, up against gravity. And then what you do is you basically just have little pans up here, or like tubes that you siphon off the hydrocarbon chains that are different lengths. So you'll have methane. Often what will happen, I think that they're cutting back on this, but back in the day, they would just burn the methane. But you'd have other hydrocarbon chains of different lengths, and you would siphon them off. And so this would be like, I don't know, kerosene and gasoline, kerosene, and then you'd have like oil, and then you'd have like other oils and tars and things like that. So different length hydrocarbon chains will come at these different levels, and you distill them out. and then you package them up and sell them for, for different reasons. Yeah, so this is the distillation process. And the same thing happens, how you can distill like water from alcohol is they have different molecular weights. And so you heat them up, you boil them, and then the lighter stuff will float up to the top, and you can siphon it off, and the heavier stuff will settle at the bottom, and then you siphon that off, and you can separate things that way. This is a physical separation of a system, as opposed to a chemical separation of a system. So the same thing happens. So the physical separation system, you have different length hydrocarbon chains, so they have different masses, so they're going to be moving at different rates. At a given energy, you have 1/2 mv squared. So temperature squiggles energy, so temperature squiggles 1/2 mv squared. And so if you have a higher velocity, then that allows you to move up against gravity to higher heights in your tower. And or you can have, so a lower mass at a fixed temperature, you have a fixed energy, which means either your mass is going to be high and your velocity small, or your velocity is going to be high and your mass is going to be small. And so the velocity tells you how high up this distillation tower you can make it, and then you just siphon off whatever the mass happens to be, and that's going to correspond to different hydrocarbon lengths. So, so that was the question about, let's see. So that is, we talked about aromatics. So that aromatics are like the ones that have the rings in them. And so that's how you get the different lengths of hydrocarbon chain that will go into your fuel. And then you basically have octane will be one of the things that you pull out, and then you can add that octane in to different amounts. You can refine the oil such that you have different octane per gram or whatever, so many grams of octane for every kilogram of fuel or something like that. And it just causes it to burn slower. Octane's harder to break apart, I think is what it is. It's harder to break apart. And so when you inject it into the fuel, the easier to break apart fuel will burn fairly quickly, but there's less of it. And so the octane kind of picks up at the end. Well, I don't know if it picks up at the end, but it because octane burns more slowly, you don't get the abrupt slamming of the pressure front, the flame front, as it slams into the piston. So inside the piston, inside the cylinder, the flame is going to initiate at the spark plug, and it's going to drive outwards. And so you have the cylinder head, or I think the head of the piston, whatever it's called, is going to be coming up, and there's going to be a shock wave or a flame front that's approaching the cylinder from the spark plug at the top. And so if it approaches very rapidly, then you'll cause damage to the cylinder, especially if the cylinder is moving towards the flame front as the flame front is advancing. And so that's when the engine pings, is that you have the flame front advancing downwards and you have the piston still moving upwards, and then you get the impact of those two things hitting each other. It's better to have the piston starting to go down as the flame front hits it, so that it reduces the impact and it doesn't wear on the engine as much. And so that's getting the timing of the ignition of the spark plug relative to the piston. So that is how diesel engines work. There's this diagram. This is animated engines that shows. So here's like the 4-stroke cylinder, and I think you can slow it down. So you draw the gas in. So you're expanding the volume, but you're not changing the pressure because the pressure is equalized to the atmosphere, roughly equalized to the atmosphere. And then you close the cylinder, and then you're going to compress the gas. And then at this point, the spark plug goes off, and then you get that flame front expanding into the cylinder. And that drives the piston down, and then you exhaust the spent fuel and the ash that you form out the back. So that's the 4-stroke thing. If you do the diesel engine, I should go back. So with the 4-stroke engine, you have to tie the spark plug you have to connect the spark plug to the motion of the piston so that the spark plug goes off at the right time. And then the spark plug is set up to this battery system, or like probably a solenoid or something like that. And so you store up energy in the car, and then at the right time, you're going to make contact that's going to discharge the spark plug. And so you have to time the ignition of the spark plug to the cycle, where the cycle is in here. And that's going to be done with some kind of timing belt. Okay, in this case, it's a gear, but you would typically do it with a timing belt. And so you have the valves themselves are driven also by where the system is in its cycle. And so you have these cams that will open or close different valves depending upon where this is in its rotation compared to where the crankshaft is in its rotation. So you have the camshaft here and you have the crankshaft here. Crankshaft is where you're getting the power from. The camshaft is just taking the spinning system, coupling it to the motion of the valves so that the valves open and close at the right time. And then you have the spark plug attached to that system as well, so that the spark happens at the right time. And it's all driven off of where in the cycle is the crankshaft. And then you just have, your gear ratio tells you how often this is going to go off. So how are the valves able to withstand the combustion stroke? They're thin and small compared to everything else. Well, they're still made out of metal. And the other thing is that the valves, they're basically designed, you can see from here the way the valves are structured. So they have this kind of tapered edge. And the valves are basically, when the stroke happens, the valves are pushed up against the top of the cylinder so that it actually seals them in place. When the gas is expanding, it seals the valves in place so that as opposed to trying to shove the valves into something and then having the pressure trying to push the valves away, the increase in pressure is actually seating the valves more securely in the little socket that they live in. Did I ever have a thought about being a medieval age and trying to build an engine? I have not done that. Some of these things are pretty ingenious how they came up with it. Some of these different engines. So this is the diesel cycle. There's a glow plug here that's already going. You'll notice that the flame front expands as the piston is expanding. If I go back to the Autocycle, if the animation is correct, then the flame front expands very quickly at the top, and before it expands all the way to the bottom. Where with the diesel cycle, it's got a much longer stroke, and anyways, it also has these cams up here that's also connected to the crankshaft. It's not showing that, but the glow plug is just glowing. There's no spark that sets it off. It's spontaneously combusting. The same thing happens with other engines. So for example, a jet engine, is this the best jet engine that they have? A jet engine operates under the same principles. Basically, you have here's the opening of the jet engine, here's the closing of the jet engine. You have a bunch of compressors up front, so you have a series of fan blades that are angled at different angles, so that when the air comes in, it gets compressed as it passes from one set of fan blades to the next. So you have half a dozen compression blades or something like that. There's a crankshaft that runs through the whole thing, and then at the back end you have another series of blades that are oriented the opposite direction. And then you have a flame that's burning right here, kind of like a pilot light. So you bring the air in, you compress it as it goes through these different so as the blades are spinning, it's compressing the air, and then it goes to another series of blades with a slightly different angle of attack, and then that also compresses the air a little bit more. And so the pressure of the air is built up inside here, and then you add the fuel and light it on fire, and you get the combustion here. The gas expands. As the gas expands, it passes through these blades at the back end that's called the turbine. So you have the compressor up the front and the turbine in the back. They're just blades, and they're all attached to the same thing. They're all attached to the same shaft. And then as the expanding gas passes through the turbines, it causes the shaft to spin. The spinning shaft causes the air to be compressed. So as you're extracting some energy from the expanding gas to drive the compressor, the rest of it is exhausted outwards, and that gives you the thrust for a jet engine. But it's the same idea. You have some volume of air that comes in here. That volume gets compressed. You're changing the chemistry of it. So here's the changing chemistry. You light it on fire. That increases the pressure as this gas expands, and then you're extracting some of that energy in the turbine in order to drive this thing in order to drive the compressor. So in some cases, you can have it drive a separate fan. So this is like just a regular jet engine. But in some cases, you can have it drive, it doesn't, oh, here. So this is a turbo fan. So you still have the compressor up front. You have the expanding gas here. You have the turbine in the back. And then the front of it is a bigger blade that acts like a propeller. So not all the air that comes into the engine goes through the combustion chamber. Some of the air just gets funneled around the sides and is pushed back as though this was a propeller. And so a turbofan, this is more efficient because you don't have to burn all the air. You don't have to use all the air in the combustion cycle, and you can capitalize on the energy that's being released through the rearrangement of the chemical bonds in order to drive this blade that adds to the thrust. So not only do you get the thrust from the expanding gas, but you get the thrust from the spinning propeller blade, or from the spinning fan inside the engine. So this is the jet engines. If you look at jet engines on like the 707, Boeing 707, you can see how small the engines are. Let me go back and get an image by itself. Compare the size of these engines to what you get with a more modern engine. If we look at the Boeing, okay, so a 737 is more modern, especially the new ones. You can see the size of those engines. They're like gigantic engines. And that's because they've added the fan. They've increased the size of the fan in the front. If you look at, I think the 7E7 or the 787, it has like even bigger engines. They're just huge. Okay, and that's because you went from a turbojet to a turbofan that has that extra stuff on it. Let's see, what's the efficiency of a jet turbofan engine compared to diesel engines? So this, I don't know the answer to that question off the top of my head. So this is running off of what's called the Brayton cycle. So this compressor turbine structure is called the Brayton cycle. So what we've seen so far is the Autocycle. We've seen the diesel cycle, D-I-E-S-E-L, and I keep spelling this. These are lower. This is like someone's actual last name. The Autocycle, the diesel cycle, again, someone's last name, and then the Brayton cycle. This is the jet engine cycle. And so there's a way of calculating what the Brayton cycle efficiency is. I don't remember what the formula is. On that same pressure volume diagram, so we have pressure here and volume here. The Brayton cycle is some like weird shape like this up there, where the diesel cycle and the Autocycle are, the diesel cycle looked like this, looked like that, and the Autocycle had the vertical line. Okay, this is not there. Ignore that part. So the diesel cycle is there. The Autocycle looks like this. Two vertical lines where the diesel cycle has a horizontal line. And these are approximate, right? It's the real life is a bit more messy than this. But the Brayton cycle is something up here. Then you have like the Rankine cycle, the steam cycle, where you have, not only are you, there's a bunch of things happening with a steam cycle. One of them is that you're actually condensing back into liquid. So you're exploiting the phase transition of the water from a fluid or from a liquid into a gas to help drive the engine. So natural gas power plants, natural gas generators run off of this Brayton cycle. Well, there's two different kinds of natural gas power plants. There's one that does the Brayton cycle only. These are peaking plants. And so if we look at the PV diagram for the Brayton cycle, Brayton cycle PV diagram. None of these look right. Okay, so anyways, here's the Brayton cycle PV diagram. It looks a lot kind of like the diesel cycle. So this is the Brayton cycle. It typically operates at kind of higher pressures, certainly at higher temperatures. And what you'll do So a natural gas power plant is basically a jet engine, and that runs off of natural gas instead of diesel fuel or instead of kerosene. And so what you can do is you can take the exhaust that comes out at high temperatures, and you can use that exhaust to drive a steam cycle, which is the Rankine cycle. I think it's spelled like this. Maybe there's an N in there, Rankine cycle. So this is the steam cycle. So Thomas the Tank Engine type stuff. And so you can take a jet engine, use the high temperature exhaust to drive a boiler and run the Rankine cycle off of that. That's called a combined cycle. So this is the most efficient natural gas power plant, is the combined cycle, where you run the jet engine and you take the exhaust from the jet engine and you run a steam cycle off of it. And these get pretty high. I don't know exactly what it is. I might as well look it up instead of guessing. I think it's like 60%. So let's go with the combined cycle efficiency. Uh, 50 to 60%, which is pretty good. When you look at the when you look at the efficiency of the Autocycle, you're more like 30%. So that's the combined cycle. Yeah, thermal plants do have a jet engine design, usually two engines pointing in opposite directions. So there you go. So the Carnot cycle, oh yeah, okay, so as long as we're on the subject, I do need to run, but as long as we're talking about it, the Carnot cycle, I'm sorry, the Wankel cycle is, where is it? It's on here somewhere. Oh, this is like this rotary one. This is like airplanes, how airplanes fly. They use the spinning of the propeller to compress the pistons. So there's an off-center hub that drives the pistons, and so you'll have your propeller blades, and as the propeller blades spin, the spinning of the propeller blades is actually what's driving the pistons, which is actually kind of interesting because animals breathe kind of like this as well. So a lot of animals, not humans, diaphragms are detached from our legs. So our breathing is independent of the rate at which our legs are moving. But other animals like horses and things like that, and rabbits, their diaphragm is actually connected to their body. So as their body expands, like stretches out and compresses as they run, that drives their lungs. And it's kind of similar to what's going on here. I don't see here's the Wankel engine. So the Wankel engine is this rotary thing. Is it Mazda? It's either Mazda or Mitsubishi that did this for a long time. So you're drawing air in, compressing it, causing it to expand, and then exhausting it. It's the same idea. You bring gas in, you compress it, you change the chemical composition, you release that energy to drive the pressure up, and then you use that extra pressure to expand the gas, and then you extract that energy from the expanding gas. So I don't remember if it was Mitsubishi or Mazda that used the Wankel engine for quite a while. So developed in the 1960s. That's kind of cool. Mazda. Okay. And then there's a variety of other different ways of. There's one that's like the oil, how you pump things with oil. The Stirling cycle. This is one that just relies on heat reservoirs. The expanding gas just from a heat reservoir, you can hold it on your hand and it will drive things. So Stirling engines are kind of interesting. They all basically rely on expanding and contracting gas and using the equation of state, the pressure-temperature relationship, to extract energy from the atmosphere, basically. Okay, there we go. Those are the different cycles of things. Which one is the Flintstones? The Flintstones was just Fred power.